So the second lecture will be an introduction to machine learning. And now we'll go more into the concepts and a little bit more about the theory behind machine learning. And the concepts that we will see will be applied tomorrow in deep learning to understand a little bit more these techniques. Okay, so first of all, machine learning is very broad. There's a lot of research done in the past, I would say, 20, 30 years in machine learning, and we have identified different types of learning. And one analogy that we can have with humans is that these models are learning with a teacher. And the concept of a feedback from a teacher is fundamental and central in machine learning. So the way we do it, the way we simulate it on a computer is that the model will make a prediction, and the teacher will compare the model prediction with the true label, with its own prediction, and give a feedback on how right was the prediction. And the model will use this feedback to improve its prediction the next time the model will see the same example. It will tune automatically some parameters so that next time I receive the same example, I will get the right answer. So one way to implement it is supervised learning. So in supervised learning, the teacher, or let's say the annotators, the person that will put the label on a data, will provide some targets as examples. And there are two categories of supervised learning. Regression, where the targets, the quantities I want to predict are real valued variable. It's a numerical value between -infinity to infinity. Or maybe I want also to predict categorical variable, and this is called classification. So categorical variable, we saw categorical variables for text. It's only one identifier associated to a concept, and I don't have any ordering between the values of a categorical variable. So there are also two different kinds of classification. So if I receive, as an example, one image, and I can only predict one concept because I know that in this image there's one and only one concept, it's called multi-class. I have, let's say, a choice among M concept, and I must only choose one as a prediction. In a multi-label setting, I receive one image. There can be multiple objects, multiple concepts in this image, and I must find all the concepts. I must predict all the concepts, which is called multi-label. And again, in supervised learning, one example will be represented as a couple, the X, the input of my model, and the Y, the output. So the next concept is about the helpfulness of the teacher. So here it's very intuitive. If I give you this image as an X, and I give you these labels, car, person, tree, and I want to do multi-label classification, you can see that the feedback from the teacher is very weak. On these images, it's very hard to see the trees, the persons, even the car here, but this is the labels that I have in my data set. And we can already see that solving this task will be difficult because the labels are not very informative. If I have another data set like this one, where you have bounding box associated to all concepts, and the concepts are linked together in this hierarchy of concepts, and you can see that even the images are connected together through this hierarchy, you have a lot more information. Here it's even more interesting. For this dataset, an image will have a bounding box that will locate the concept, and there will be a description in English of this concept. So maybe I can also use this information in my model to implement the task. So we have different level of informativeness associated to labels. And this is more high quality labels. And here we can see it's more noisy, more low quality. But the work required to annotate with this degrees of details can be important. So another type of learning and another concept related to teacher is active versus passive learning. So in supervised learning, I just receive a data set that has been annotated by the teacher, and then the teacher, I don't see the teacher anymore. I just use the labels to encode the knowledge of the teacher. And I will use a learning algorithm that will work on this labeled data set and will optimize the parameters. And I will use the experimental protocol that we have seen in the first presentation to evaluate the model. But there's also another framework, which is active learning. And in active learning, I can use unlabeled data. So very often you will have few labeled data, few examples that have been labeled by expert, but a lot of unlabeled data. And what I can do with these unlabeled data is to provide one example to the model, and the model will provide me a probability at the output. And I can use this probability to interpret how sure the model is about the prediction. If I have two classes and the model predicts 0.5 for one class and 0.5 for the second class, the model cannot distinguish between the two classes. It means that the model is uncertain about this example. And I can ask to a teacher, to a human annotator, to provide the label for this example. And this is a good strategy. And after that, I will add the label example to the label dataset. And it's a good strategy to find examples that are tricky for the model, because the model is uncertain on these examples. For other unlabeled examples where the model is very sure about the prediction, I will not try to annotate these data. So active learning, I'm talking about it because I saw that platforms like SageMaker by Amazon are now implementing active learning. So you can use this technology to reduce the amount of labeled data the amount of data that you must label. It's interesting to look at it. Another type of learning is unsupervised learning, and there's a lot of research on unsupervised learning. And it's a little bit more difficult to really define what is unsupervised learning because it has evolved over time. But for deep learning, it's really about trying to learn some representation that will be useful for any other class, for any other task afterward. So what does it mean? It means that, let's say that I have some text. I will create a task that does not require any label, and I will train a model to achieve this task, and I hope that the representation that will be learned by the model will be useful after that for the task that I am interested in. And it will depend on the kind of data that you use. So as a task of unsupervised learning, if I have document, I can train a model to, given previous words, I will predict the next word. I don't have any label on text to train a model to do it. The model is just trying to predict what will be the next word in a sentence. So it's a we can say that it's a universal task. For images, I can remove some pixel of the image or add noise to the pixels, and I will train a model that will try to reconstruct the image, remove the noise. And one task that I think is interesting for video is I give a video to the model, and the model must predict if the video is in the right order or in the reverse order, which can be very hard to do to train a model to do so, because the features required to predict the arrow of time in a video is something that is complex to learn, these features. But if I have these features, maybe I can use this architecture for another task. And most of the work today are about probabilistic modeling of high-dimensional data with deep learning, how to predict a probability associated to high-dimensional data. So if I model a probability, I can take my data and generate some cluster. I can clusterize my data, and I will have the probability to belong to a cluster, and this is called clustering. And so if I have a cluster of data that are similar, maybe I can just use one label for my test, assign it to the cluster, and the label will propagate over all the cluster, and so I'm using less label for my test. But it's hard to do this clustering. Also, if you have a good model to do clustering, maybe you will receive a new data point, and the data point will be alone far from any cluster, and we can do anomaly detection by it. It's a new data point that is totally different from what I have seen in my training data set. And from a probabilistic model, I can model the probability associated to the data, but I can also sample from this probability distribution. And this is what people have been doing with deep learning for 4 years now with GAN models or autoregressive models, etc. It's called data generation. So here you have a probabilistic model. This model really tried to assign a probability to any photos of face. And after I have trained my model to represent the probability of face in the nature, I can try to sample from this probability to obtain new faces. And these faces does not exist. These people does not exist in reality. They have been sampled from my probabilistic model over images. I can do the same thing for speech, but also for text synthesis. So there was a new model by OpenAI called GPT-2, and the model is creating a whole new story about unicorns that have been discovered in South America, and you have a scientist that is giving an intuition on some understanding about this new creature. And the reason why this story has been generated by the model is because it has been trained on a lot of stories of unicorns, of course. And now we have a probability distribution over text. And the story was pretty convincing. It was so convincing that they were afraid to release the model at the beginning because people can use this model to generate fake news. Also, data generation are used to learn a simulator. So if I want to train a model to perform action with a robot, so the model is inside the robot and the robot is making some action with the actuators, it's much cheaper to learn with deep learning a simulator of the robot, so the model can simulate some actions and then deploy the model inside the real robot in a physical world. Because doing the simulation inside the neural network would be much faster than in reality. And unsupervised learning can also be applied to semi-supervised learning, which is really about using these universal tasks here to learn representation that will be universal and useful for any task that you can think of. And there is a lot of progress in semi-supervised learning since 6 months. This is evolving very, very quickly, and they believe that the techniques in supervised learning can be applied in industry in a very short term. Okay, so another type of learning is the way I provide an example to my model. So if we are doing online learning, I take one example in my dataset, I give it to the model will tune its parameter, and now I discard this example. It's like I have a very small memory associated to my model, and I must really deal with the data on the fly. For application where we have a huge flow of data, it can be necessary to use online learning. That's why people were doing research on this. But in deep learning, where it's very costly to acquire labels for your data, what you want to do is batch learning. So batch learning, I will have a memory where I will stack a lot of training example, labeled training example, and the model will iterate over this batch over and over until it has a good performance on the validation set. And so most of the talks that you will see this week are about supervised statistical batch learning with a passive learning algorithm. It's a very long description. It's only to tell you that there's a lot of different concepts in machine learning, and deep learning is a tiny part of it that is very important today. And that we can use we can do, as an example, online learning for deep learning. People are looking at this question, but it doesn't work very well for now.